The DESI Shockwave. Dark energy is not constant. The universe is breaking its own rules. The moment the data came in, the room fell silent. For months, the DESI team had been mapping galaxies across the cosmos, 15 million of them, building a detailed 3D snapshot of how the universe had expanded over billions of years. But when they plotted the results, the numbers didn't match what physics had promised. The equations that once fit perfectly now misfired, just enough to whisper something impossible. Dark energy, the force driving the universe's acceleration, might not be constant after all. The universe, it seemed, was breaking its own rules. For cosmologists, this is the kind of discovery that stops time. Everything, the lectures, the theories, the models, had been built on the assumption that dark energy was a fixed property of space itself, unchanging, steady. And suddenly, DESI's data implied that it might be changing, evolving, slipping through the cracks of the laws we thought we understood. Across observatories around the world, researchers checked, rechecked, and reran the analysis, hunting for errors that weren't there. The universe is supposed to make sense, but suddenly it doesn't. It wasn't supposed to be this way. Back in 1998, the idea of dark energy was born from the light of dying stars. Two separate teams studying Type Ia supernovae, the most reliable cosmic yardsticks, found something that defied expectation. The further back they looked, the faster galaxies were moving apart. Instead of slowing down under gravity, the expansion of the universe was speeding up. It was like throwing a ball into the air and watching it accelerate upward into nothingness. That discovery shook physics to its core, earning the scientists a Nobel Prize and setting the stage for a new cosmic paradigm. Einstein's cosmological constant, once dismissed as his greatest mistake, suddenly returned as the simplest explanation. Maybe physicists thought empty space wasn't truly empty. Maybe it contained a built-in pressure, an intrinsic energy that pushed the cosmos apart. They called it the cosmological constant, symbolized by the Greek letter lambda. Combined with cold dark matter, it became the foundation of modern cosmology, the lambdictum model. Lambdictum worked. It explained the cosmic microwave background, galaxy distributions, the large-scale structure of the universe, all of it. For a while, it seemed perfect. Science loves a model that fits everything neatly, but beneath that elegance lurked unease. The cosmological constant was absurdly small, 120 orders of magnitude smaller than predicted by quantum theory, and nobody could explain why. It looked fine on paper, yet it felt like balancing the universe on the head of a pin. For decades, that unease stayed in the background. Cosmologists told themselves the details would work out later. Lambdictum was too successful to abandon, too elegant to doubt, until now. Because DESI's results don't just hint at a crack in the model, they suggest the crack is alive, growing. The expansion rate appears to shift slightly over time, a sign that dark energy's strength may be evolving. If that's true, then every timeline for the universe's future, from endless expansion to eventual collapse, needs rewriting. This isn't just academic confusion. This could decide how the universe ends. Whether space stretches into an infinite cold darkness, or one day collapses in on itself in a fiery, big crunch. And right now, one thing is clear. If dark energy isn't constant, then the rules we trusted to describe the cosmos were never rules at all, just temporary agreements that the universe has decided to break. The moment the universe started accelerating. It began, as great revolutions in science often do, with a mistake that refused to vanish. In the late 199s, astronomers were chasing a simple question: how fast is the universe slowing down? Everyone knew gravity had to be tugging on galaxies, gradually pulling the expansion that began with the Big Bang back towards stillness. All they needed were precise distances and velocities, measured from the light of distant supernovae. Straightforward, routine work, until the universe told them otherwise. By 1998, two competing research groups, the Supernova Cosmology Project and the HISE Supernova Search Team had independently reached the same stupefying conclusion. The universe wasn't slowing down at all. It was speeding up. Those brilliant points of light, dying stars exploding halfway across the cosmos, appeared dimmer than expected. The dimness meant they were farther away than gravity alone could explain. Somehow, the expansion of space had begun to accelerate. For a moment, no one wanted to believe it. There had to be dust, measurement bias, something mundane. But the data held. And when those results were announced, it was as if cosmology's solid ground cracked open beneath its own feet. Decades of assumption, the very notion that gravity ruled the cosmos, suddenly needed rewriting. This discovery didn't just add a puzzle piece, it changed the entire picture. To explain that runaway expansion, physicists invoked a strange idea once abandoned by Einstein, the cosmological constant. He'd introduced it back in 1917 to keep the universe static, then discarded it when Hubble's observations proved cosmic expansion. Now, in a twist of historical irony, the biggest mistake of Einstein's career became physics' most useful rescue line. The Lambda model, Lambda Cold Dark Matter, was born from that rescue. Lambda represented the cosmological constant, a uniform energy density that filled all of space, exerting a gentle but persistent push outward. Cold dark matter accounted for the unseen mass holding galaxies together. Combined, they produced a beautifully simple equation that matched nearly every observation available: the temperature ripples of the cosmic microwave background, the formation of galaxies, the clustering of matter across billions of light years. Suddenly, everything fit. For the first time, cosmologists felt they had a complete story. A universe composed mostly of dark energy, about 70%, plus dark matter and a small dose of ordinary atoms. Gravity pulled, dark energy pushed, and the cosmic expansion balanced perfectly between them. There was elegance in that balance, the kind scientists crave, a minimal model that explained a maximal universe. Still, even in those triumphant moments, whispers of unease lingered in the margins. When theoretical physicists tried to compute the energy of empty space from quantum mechanics, they ended up with a number 120 orders of magnitude larger than what cosmology observed. It was an absurd mismatch, so profound it became known simply as the cosmological constant problem. Something fundamental had to be wrong, but no one could tell what. Then came another irritation, the coincidence problem. Why in this exact cosmic moment were dark energy and matter so close in strength? Billions of years earlier, matter dominated. Billions of years from now, dark energy would. Yet somehow, right now, they appeared almost equal, like a cosmic coincidence timed for our viewing. The odds felt ridiculous, like catching the universe mid-sentence. Still, the Lambda model worked too well to abandon. It became cosmology's bedrock, taught in textbooks, carved into simulations, used to predict everything from galaxy formation to cosmic background radiation. Scientists learned to live with its discomforts the way sailors adjust to a persistent creak in the hull, a noise that never sinks the ship, so long as the voyage stays smooth. For 2 decades, the voyage did stay smooth. Observations refined parameters. Satellites like WMAP and Planck confirmed the model's accuracy to astonishing precision. Graphs lined up. Predictions matched measurements. The universe appeared predictable again. That nagging unease slipped into the background. And yet, even as lambdictum reigned, some astronomers couldn't ignore subtle tensions forming on the edges. The Hubble constant, the rate of cosmic expansion, came out slightly higher when measured from nearby galaxies, and slightly lower when inferred from the early universe. The discrepancy wasn't dramatic, but it refused to disappear no matter how data improved. Something in the model might be missing. In hushed conference corridors, scientists wondered if dark energy itself could evolve, its strength changing over billions of years like a fading heartbeat of the cosmos. It felt speculative, bordering on heresy. After all, Lambda was supposed to be constant by definition. But a few dissenting researchers built models anyway, quintessence, phantom energy, dynamic fields that rolled or fluctuated over time. These remained theoretical curiosities, waiting for data precise enough to prove or dismiss them. Years passed, telescopes grew sharper, surveys mapped ever larger swaths of sky. Each improvement reaffirmed lambdactum, or seemed to. Then a new instrument appeared, designed from the ground up to test the universe's expansion with unrivaled accuracy. The Dark Energy Spectroscopic Instrument, or DESI. DESI wasn't designed to explore philosophy. It was built to measure reality at scale. Mounted on a telescope in Arizona, it would capture the light from tens of millions of galaxies, creating the most detailed 3D map of the universe ever assembled. The goal was simple: trace how cosmic structures evolved over 11 billion years. Hidden within that map, cosmologists hoped, lay the fingerprint of dark energy's behavior, constant or changing. No one expected surprises. DESI was meant to confirm the model everyone already trusted, to sharpen its numbers, not question its core. But the universe, as it has proved more than once, refuses to stay in its assigned box. For decades, physicists thought the mystery of 1998 had been solved by lambdactum, a neat harmony between gravity and vacuum. What they didn't know was that this harmony might only be temporary. DESI's data would soon reveal subtle variations in the expansion rate, as if the push of dark energy had changed strength over time. The very thing Einstein and modern cosmology had labeled constant began to look alive. For 20 years, the story of dark energy felt complete. Now, the sequel was writing itself, and no one knew how it would end. DESI, the map that shook science. In the high desert of Arizona, on a moonless night, a massive instrument hums quietly against the starlit sky. It's perched atop the Mayall telescope at Kitt Peak National Observatory, an array of 2-meter-wide glass mirrors and nearly 5,000 robotic fiber cables, each one aligned with surgical precision to target a single galaxy. The machine's name is DESI, the Dark Energy Spectroscopic Instrument, and its mission sounds impossibly ambitious: to map the structure of the universe in 3 dimensions, across 11 billion years of cosmic history. Every clear night, DESI points outward and captures the faintest glimmers from galaxies so distant their light began traveling long before our planet existed. Each light trace carries a fingerprint, a redshift, that reveals not only how far away the galaxy lies, but how fast it's moving due to the universe's expansion. Multiply that by 15 million galaxies and a few 100,000 quasars, and you don't just get a map. You get a time machine, one that records the history of cosmic expansion in exquisite detail. Scientists call it the largest 3D map of the cosmos ever made. Yet when they began to assemble those swaths of data, what emerged wasn't a simple confirmation of known physics. It was an echo of something no one had expected. DESI didn't just measure how galaxies were scattered through space. It measured how the universe stretched between them. And hidden deep in the correlations of those measurements lay a signal that would shake cosmology to its core. The technique DESI used relies on a kind of cosmic relic, baryon acoustic oscillations, or BAOs. Billions of years ago, before the universe became transparent, the cosmos was a hot plasma of light and matter. Sound waves rippled through it, pushing matter outwards in tiny shells. When the universe cooled around 380,000 years after the Big Bang, those waves froze in place, leaving an imprint, a preferred distance scale, of about 480 million light-years. Think of it as the faint fossil of early universe sound, embedded in the large-scale pattern of galaxies today. That pattern gives scientists a cosmic ruler. By measuring the separation between galaxies across different times, they can see how the universe's expansion has changed. If dark energy were truly constant, the stretching should follow a smooth, predictable curve. But DESI's data didn't quite obey that script. The measurements implied a slight drift, a subtle evolution in dark energy's equation of state, its balance between energy and pressure. In plain terms, it looked as if dark energy's strength was changing. At first, the team thought they'd miscalculated. Instruments this sensitive are notorious for small biases. Even a calibration error in one fiber could produce misleading results. So they reprocessed everything, dozens of times. They cross-checked with supernova data, with cosmic microwave background predictions, with previous bow measurements. The anomaly refused to vanish. It grew more convincing. When the final statistical analysis came through, the message was unmistakable. DESI's second major data release revealed a 4.2 sigma preference, about 99.995% confidence, for evolving dark energy over the traditional cosmological constant. It still fell short of the 5 sigma gold standard physicists' demand for a confirmed discovery, but it was high enough to make every cosmologist stop and stare. Numbers rarely inspire gasps, but in collaboration meetings, scientists sat speechless. Some asked if the equipment had drifted, others quietly wondered if the universe itself had. For nearly 30 years, Lambda had described every major observation, from the microwave background to galaxy clustering. Now this instrument, designed to verify that model's precision, seemed to be rewriting its foundation instead. The weight of the finding rippled through the scientific community. DESI wasn't some fringe project. It was a billion-dollar international collaboration involving hundreds of astrophysicists and data analysts. Every member understood how enormous the implications were. If dark energy isn't constant, then Einstein's cosmological constant isn't the full story, and the universe's long-term future might look radically different from what textbooks describe. Press offices prepared cautious language. Officially, they called it a statistically significant indication of dynamical dark energy. Unofficially, in hallway conversations and late-night calls, physicists admitted what they privately felt. This was the first real hint that the standard model of cosmology might be incomplete. Some were thrilled, others uneasy. Many simply stared at the results, trying to grasp their meaning. The power of DESI lies not just in how many galaxies it observes, but in the precision of its distance measurements. Each of those faint smudges of light acts as a marker in space. By assembling them, DESI reconstructs a cosmic web, a vast lattice of filaments and voids stretching across billions of light years. In that web's geometry lies the expansion history of the universe. What the team found was that at specific redshifts, corresponding to different cosmic eras, the web appeared slightly more stretched or compressed than Lambda predicted. The deviation wasn't random. It followed a smooth, time-dependent pattern. If the trend holds as more data arrives, it suggests that dark energy's effect grows stronger or weaker depending on epoch. That single detail transforms every projection cosmologists have made for the universe's fate. In the constant Lambda model, dark energy remains unchanged forever, driving infinite acceleration, a cold, lonely heat death. But an evolving form of dark energy could change course, perhaps weakening enough to allow gravity to regain control. In that case, the universe's expansion might slow, halt, or even reverse into a catastrophic collapse. For the first time in 2 decades, both outcomes looked plausible again. One researcher put it bluntly during a conference Q&A. If this result survives verification, the universe might not be heading for an eternal freeze. It could one day fall back in on itself. The room fell still. The words hung there, a reminder that no matter how abstract cosmology feels, its consequences apply to everything that exists. And yet, amid the shock, all began to creep in. The idea that an array of tiny fiber optic cables could capture a signal stretching from the dawn of time to the present day was dizzying. DESI wasn't inventing new laws. It was listening to whispers encoded in starlight, whispers that had traveled billions of years to say, "You don't know me as well as you think." For now, no one's rewriting physics textbooks. DESI's significance remains immense but provisional, awaiting independent confirmation from upcoming missions like Euclid and the Rubin Observatory. Still, the 4.2 sigma mark feels like a tremor before a quake. It's a data point strong enough to demand attention and strange enough to provoke fear. A reminder that even the universe's most established truths can fracture under the right kind of scrutiny. Behind the scenes, researchers talk about horizons. A few percent drift in dark energy's parameters might seem trivial, but extrapolated across cosmic timescales, it's revolutionary. Each new galaxy DESI logs adds another pulse to the universe's heartbeat, revealing variations that might one day map not just its expansion, but its destiny. It's precisely that long game that makes every new measurement so potent. In a scientific field often limited by what we can't see, DESI is showing that what we can see is shocking enough. As the 3D map expands nightly, catalogs fill with coordinates, dots representing galaxies that collectively tell the story of everything ever made. Somewhere in those patterns, the universe is leaving breadcrumbs about its own design and maybe its end. For decades, cosmology's greatest mystery hid in plain sight, disguised as a constant. Now, under DESI's watchful gaze, that constant appears to be shifting, quietly, insistently, as though reminding humanity that nothing, not even the emptiness between stars, stays the same forever. For centuries, science has chased the moment when the universe began. Now it's confronting the possibility that something as subtle as a change in dark energy might dictate how the universe will end. If DESI is right, our understanding of reality itself is entering a new phase, one where the cosmos grows not colder but stranger, revealing that even its emptiest spaces are alive with forces still evolving. And so, in one sweep of sky after another, DESI continues its watch, charting the shape of everything, while scientists brace for the possibility that the map they've been drawing isn't just describing the universe. It's proving that the universe is still changing the rules as we go. The universe's fate flipped on its head. For 25 years, the story of the universe's ending had been simple. Dark energy, steady and relentless, would keep pushing galaxies farther apart until stars burned out, matter decayed, and the cosmos froze in silence. It was called the heat death, a bleak but predictable forever. Every cosmology textbook sketched that same slow fade into black. Then DESI's data changed the plot. It didn't just challenge a number or a formula. It detonated the sense of certainty physicists had lived with for a generation. Because if dark energy isn't constant, if it's fading even slightly, then that eternal freeze might never happen. The cosmos could one day stop expanding altogether. Worse, it could start collapsing. To picture what that means, you have to remember how fragile cosmic balance really is. For 13.8 billion years, gravity and expansion have wrestled, evenly matched. Gravity pulls matter inward, dark energy pushes space outward. In lambdactum, dark energy always wins because its pressure stays constant while matter thins out. But if that pressure weakens with time, gravity could slowly begin to claw its way back. The scales could tilt. It wouldn't happen fast. There'd be no sudden reversal, no galaxy screeching to a halt. Billions of years might pass with nothing obviously wrong. But somewhere on unimaginable timescales, expansion would slow, not stop, just ease back. Distances between galaxy clusters would grow at a crawl instead of a sprint. Cosmic acceleration would stall. Observatories in that far future would notice the faintest change first. Redshift shrinking, light curves tightening. A quiet warning that the push of dark energy was losing strength. If that decline kept going, gravity would finally regain control. The same force that assembled galaxies would pull the universe back together. Stars, long dead by then, would trace shrinking orbits through the dark. Galaxies would begin to drift toward one another again, merging in colossal collisions. Over eons, the great web of cosmic structure would reverse itself, threads tightening, voids collapsing, everything drawn inward. Astrophysicists call it the Big Crunch. It's a mirror of the Big Bang, space contracting instead of expanding, heating as it compresses. In the final moments, galaxies would blend into a blinding plasma soup. Temperatures would spike. Quantum processes would unravel atoms. Eventually, every point in space would rush toward every other, time itself squeezing to nothing. Then, perhaps, another bang, another cycle. That's the extreme scenario. Most cosmologists still think a total reversal is unlikely, but DESI's hint of evolving dark energy opens the door, mathematically at least. If the parameter that describes dark energy's pressure, what physicists call W, rises above -1, expansion stays endless. If W slips below -1, it intensifies into a big rip, where even atoms come apart. But if W edges upward toward 0, the expansion weakens, and the big crunch returns to the table. DESI's numbers don't pick a side yet. They just say W might not be fixed. And that uncertainty is enough to turn cosmology upside down. In Princeton and Paris and Tokyo, theorists began recalculating cosmic futures. Each variation produced a different fate: slow freezes, rapid burns, collapses, oscillating universes. No two looked alike. The comforting symmetry of a constant lambda vanished. The universe's story was no longer written in one line. It became a choose-your-own apocalypse. This wasn't how the field was supposed to feel. Cosmology had finally found peace after decades of chaos. Now that peace was fracturing again. In meetings, the mood swung between fascination and dread. Someone would pull up the chart of expansion history, that beautiful smooth arc, and overlay DESI's curve. A slightly different slope, just enough to bend the end of time itself. One astrophysicist described it perfectly. We used to think the universe was coasting into a calm old age. Now we're not so sure it survives at all. For the public, nothing seems different. The night sky still looks infinite, stars still rise and fade. But for the scientists processing these results, the emotional weight is immense. Many dedicated their careers to refining lambdictum parameters, believing the equations described a stable eternity. Now, they're facing the idea that their universe has an expiration date, and worse, they don't know which one. Some picture the big crunch vividly. First, the long twilight, galaxies too distant to see, intergalactic gas cooling until space itself goes nearly dark. Then gravity's slow reawakening, clusters drawing together by fractions of a millimeter per century. Millions of generations later, sky maps filling again with merging galaxies. Eventually, the temperature of space skyrocketing as compression ignites new bursts of radiation. And finally, a cosmic implosion, everything everywhere, heating into one last flash. Others imagine a subtler fate, where dark energy morphs into something new, a hidden field that oscillates, giving rise to cycles of expansion and contraction without total collapse. In that picture, the cosmos breathes, eternally pulsing. Even that idea, as poetic as it sounds, would rewrite nearly all theoretical physics. Either way, the message is the same. The future isn't settled. The data that began as a statistical anomaly now hints at a living, changing vacuum, the very fabric of reality in motion. This realization hits harder than any doomsday prophecy because it's not superstition, it's measurement. The same precision that once proved cosmic acceleration is now questioning its permanence. The fear is that the end of the universe is near. It's that we can no longer describe it with confidence. What happens to science when the sky itself stops obeying the simplest constant in the book? That's the question echoing through every observatory after DESI's release. For the first time since the Einstein era, cosmologists don't just wonder how the universe began. They're forced to wonder if it knows where it's going. And that uncertainty may be the most profound shift of all. The models haven't just changed the equations, they've changed our relationship with the cosmos. We went from predicting its future to realizing it might be unpredictable. The universe has always evolved, but now, so have the rules we use to understand it. Somewhere beyond the reach of the instruments still scanning the heavens, space itself is deciding whether to stretch forever or fold back in. And here we are, small observers caught mid-sentence, watching the numbers swing slightly off course, knowing they point to an ending we still can't name. the cosmic structures that shouldn't exist. When the DESI results hit preprint servers, most attention went to the word evolving. Scientists debated the changing strength of dark energy, the equations of state, the statistical confidence levels. But quietly, tucked within the data tables, another story began to unfold, one written not in numbers but in structures. Galaxies, clusters, the vast cosmic web that stretches across light years of nothingness. Supercomputer simulations started to show something odd. Under the evolving dark energy models that best fit DESI's data, the universe forms too many massive clusters, as if gravity's grip has tightened. It wasn't a small difference. In one analysis, using parameters slightly adjusted from lambdacom, the early universe produced up to 70% more heavy clusters than standard models predicted. That's a staggering excess, like expecting a universe of pebbles and finding it filled with boulders. To cosmologists, that kind of discrepancy isn't just unexpected, it's alarming. Large-scale structure is one of the strongest tests of any cosmological theory. If dark energy really evolves, it doesn't just alter distant expansion rates. It changes how matter assembles, how galaxies are born, how clusters grow. The universe's scaffolding itself would look different. Simulations run on Japan's Fugaku supercomputer gave an early glimpse into this shifting cosmic architecture. Researchers entered DESI-inspired parameters, a slightly higher matter density, about 10% above the usual value, and a dark energy component whose pressure changed gently with time. When the virtual universe evolved, the results were unmistakable. Filaments thickened faster, gravity pulled harder, and massive galaxy clusters appeared earlier and in greater numbers. The cosmic web, usually delicate and evenly laced, became a bit more muscular, like a blueprint drawn with heavier ink. At first, no one knew how to interpret it. More clusters could mean a stronger gravitational pull overall, but the equations said the additional mass came indirectly from how dark energy interacts with matter. That interaction, small but persistent, subtly alters the cosmic balance. In some formulations, dark energy exchanges energy or momentum with dark matter, affecting how fast gravitational wells can deepen. Cosmologists call this the dark sector interaction hypothesis. Picture it this way. In standard lambdacom, dark matter builds structure freely while dark energy sits in the background stretching space evenly. In the interacting model, the two aren't strangers, they tug on each other. When dark energy steals a bit of momentum from dark matter, clustering slows. When it gives some back, structure formation surges. The result can look chaotic, regions appearing denser, others weaker, a cosmic dance where the partner steps keep changing. That balancing act might explain what DESI hinted at. A 10% higher matter density amplifies gravity's glue, encouraging earlier cluster formation. But the evolving dark energy adds a countervailing drag that later suppresses small-scale growth. The overall effect: a universe momentarily overachieving in structure, bursting with heavy clusters before settling into a slower rhythm. When these findings circulated through the cosmology community, they triggered long email threads filled with disbelief. "This can't be right," one researcher wrote. "We shouldn't be seeing more structure with less effective energy." Yet the pattern reappeared across multiple independent codes. Astronomers watching the simulations saw galaxies linking together into networks more intricate than the constants of physics would allow. Some half-jokingly called them forbidden clusters. But the joke carried an edge, because if such clusters truly exist, observed in deep surveys now underway, they would confirm that the vacuum itself, the invisible engine of expansion, has turned dynamic. It's one thing to watch data hint at evolving dark energy in graphs. It's another to see its footprints in the actual shape of the cosmos. The emotional shift was palpable. Cosmologists, long comfortable modeling the universe as an elegant equation, realized they might be watching it rewrite itself in real time. Each cluster photographed by DESI became both evidence and challenge. The structure of the universe, supposedly frozen by well-behaved physics, now looked like something alive. Late nights at observatories turned contemplative. Graduate students pointed at the evolving maps and whispered lines borrowed from old lectures. The universe is expanding, but its bones are moving too. No one could shake the feeling that they were glimpsing motion on an impossible scale, galaxies drawn toward invisible influences no constant could explain. In theory meetings, researchers swapped hypotheses. Maybe dark energy and dark matter share a common origin, a single field that split as the universe cooled, now reconnecting. Maybe quantum fluctuations ripple through the vacuum, modulating cosmic pressure like tides. Each idea sounded improbable until someone pulled up the new simulation sheets showing those overgrown clusters staring back. The cosmos, it seemed, kept rewarding imagination over restraint. The implications run deep. If dark energy can interact with matter, it can change how light travels, how supernovae appear, even how gravitational waves propagate. Entire calibration methods would need re-evaluation. The distance measures anchoring the cosmic ladder might shift slightly, cascading into fresh interpretations of Hubble tension and structure growth anomalies. Every precision claim in modern cosmology would need an asterisk. Yet amid the technical upheaval, there's wonder too. Visualizations from the Fugaku runs reveal an evolving universe almost cinematic in motion. Filaments glow as clusters coalesce, voids collapse into new bridges, flows of matter ripple along corridors of gravity. When rendered at high speed, it looks disturbingly organic, a brain firing with cosmic synapses, sparks of creation and constraint alternating through deep time. The models even suggest feedback loops. As energy transfers between the dark components, expansion modulates, which in turn alters how subsequent clusters grow. The universe becomes a feedback system, adjusting itself as it ages. Watching those animations, one researcher muttered, "It's like the cosmos is breathing." That line made its way into presentations, half metaphor, half possibility. Maybe what we call dark energy isn't an external force at all. Maybe it's the pulse of space itself, a fluctuating tension that reacts to its own structures. If that's true, the laws of physics aren't rigid. They're relational, tied to the evolving cosmos they describe. The thought is unsettling. For centuries, science has sought constants, numbers immune to time. But DESI's hints and the structures they inspire suggest a different kind of reality, one in which even the constants learn. The more accurately we measure, the more variability we uncover, as though precision itself reveals motion. Standing inside that paradox, cosmologists admit all more than frustration. They're witnessing theory lose its grip gracefully, replaced not by chaos but by complexity. Every unexplained cluster becomes a message. The universe is more adaptive than we imagined. Before DESI, the cosmic web was just background, an elegant scaffolding that cradled galaxies. Now it's evidence of a negotiation between the deepest forces imaginable. Each filament is a record of that conversation, written across billions of light years. So when astronomers talk about structures that shouldn't exist, they're not really saying the cosmos broke its rules. They're saying the rules were never static in the first place. In the faint light from those clusters, we're watching the universe evolve not just in time and size, but in law and logic, rewriting itself while we're still trying to read the old script. The crisis within physics. To understand why DESI's findings feel like a crisis, you have to see what it means to challenge lambdactum from inside its own walls. For more than 2 decades, this model wasn't just a theory. It was the foundation of modern cosmology. It explained almost everything observable with astonishing precision. The cosmic microwave background, galaxy clustering, even the faint distortions of space-time caused by dark matter. Physicists trusted it the way sailors trust a compass, not because they couldn't imagine it failing, but because it never had. Lambdactum's success made it sacred. The model's 6 parameters, refined through missions like WMAP and Planck, were rehearsed so often that scientists could quote them from memory. Papers began with variations of the same phrase, within the lambdactum framework, as though there were no credible alternative. The field's rhythm matched the model's confidence. Publish, confirm, refine, repeat. For years, that stability felt like progress itself. Then DESI arrived and the numbers started whispering betrayal. The expansion curve deviated where it shouldn't. The equation of state parameter, W, wandered from its tidy value of -1. That shift did more than bend a line on a graph. It bent decades of certainty. Suddenly, cosmologists faced an unthinkable scenario. The universe may not obey the equations that made physics look invincible. The discomfort echoes deeper than most outside the field realize. Lambdactum intertwines with the basic structure of general relativity and quantum field theory, the twin pillars of physics. Those pillars never talk nicely to each other. Quantum theory predicts a vacuum energy density so enormous it would blow the universe apart, while general relativity only requires a whisper of that energy to match observations. The difference between prediction and reality is the worst mismatch in science, roughly 1 part in 10 to the 120th. To patch it, cosmologists called the leftover a cosmological constant and moved on. Lambdactum was their peace treaty between contradictory worldviews. DESI threatens to tear that treaty in half. If dark energy isn't constant, it means the vacuum's energy changes over time. That can't happen within the tidy framework of quantum fields unless something fundamental, something about the very fabric of spacetime, is wrong. The equations can't accommodate it without mutation. So physicists find themselves in a corner where the math demands revision, but refuses to say what kind. The questions spill out like dominoes. If the vacuum is evolving, what drives it? A new field? An interaction hidden in the early universe? If that same process affects matter density, does it leak energy between the cosmic components? Every possibility opens another unresolved tension, another parameter that suddenly looks suspect. Even before DESI, small cracks had formed. The Hubble tension, a persistent mismatch between local and early universe expansion rates, has hovered around a 5 km/s discrepancy for years. The structure-growth tension, describing how quickly galaxies clump under gravity, shows a similar inconsistency. Taken alone, each could be dismissed as measurement error. Together, they began to sound like a pattern. DESI's evidence for evolving dark energy doesn't just add to that pattern. It weaves the cracks into one possible cause. At conferences after the 2025 data release, the mood shifted from disbelief to confrontation. Panels filled with graphs showing overlapping distributions. One curve for lambdactum, another for dynamic dark energy. They barely diverged, the difference subtle but relentless. Physicists who'd spent their careers defending the standard model found themselves using hedged phrases. If confirmed, potential departure, mild evolution. Behind those words, an anxiety that professionalism can't hide. What if the standard model is unraveling at the edges? For theoretical physicists, that anxiety hits personal. The cosmological constant problem has been the universe's cruel joke for half a century. They've tolerated the absurd fine-tuning only because the constant at least stayed constant. Now even that mercy looks gone. If lambda evolves, then the neat cancellation that made reality stable turns into a moving target, a balance that must readjust every cosmic epoch. It's an engineering nightmare. Either some unknown mechanism keeps recalibrating the vacuum, or the vacuum is alive in ways we don't yet comprehend. Both options break something fundamental. The deeper you follow it, the stranger it gets. Quantum field theory treats vacuum fluctuations as temporary, particles popping in and out of existence across spacetime. If dark energy evolves, maybe those fluctuations develop long-term behavior, coherence on cosmic scales. That would merge the microscopic and macroscopic realms that physics has long tried to keep apart. Suddenly cosmology becomes quantum again, and every assumption about separations of scale collapses. Even observational cosmologists, usually insulated from such theorizing, feel the impact. Their entire calibration pipeline assumes lambda's constancy. Supernova studies, cosmic lensing, distance ladders, all rely on fixed reference curves derived from lambdactum. If that background shifts by even a few percent, every derived parameter changes. It's not a tweak, it's a rebuild. Precision cosmology would need to reinvent its rulers. Some senior scientists resist that prospect outright. To them, DESI's 4.2 sigma result is intriguing but not decisive. The data are early, they insist in interviews. Systematics could explain it. They remind younger colleagues how many would-be revolutions in physics evaporated under higher quality measurements. Yet skeptics face their own dilemma. The pattern aligns across independent datasets, supernovae, CMB, lensing surveys. Repetition lends credibility. Coincidences grow costly. Privately, a few admit fatigue more than doubt. They've watched physics endure crises before, relativity challenging Newton, quantum mechanics dissolving determinism, inflation rewriting the Big Bang. Each time, theory bent but didn't break. Maybe this one will bend too, towards some modified gravity model or a dynamic scalar field conveniently matching the data. Maybe the fabric of reality will accommodate another patch. But nobody can say how many patches a theory can take before it's a quilt of guesswork. You can sense the unease in scientific language. Terms like tension, anomaly, and preferred model replace the word wrong. Cosmologists rarely say wrong. It implies something almost emotional, a betrayal by the cosmos itself. But listen closely, and that's exactly what's happening. The universe is rejecting our neat symmetry, exposing how deeply we mistook consistency for truth. One theorist summed it up during a late-night symposium. Physics has no theory big enough to hold this. He wasn't exaggerating. Dark energy, gravity, quantum fields, these were supposed to be separate arenas, each obeying its rules. Now DESI's hint forces them into the same room with no translation. To explain an evolving vacuum, you can't avoid merging quantum theory and relativity, the two languages that still refuse to converse. That's not just a cosmology problem, it's a physics problem of the highest order. Young researchers find the situation oddly liberating. For the first time in years, cosmology feels open. There's room again for discovery instead of precision tuning. Grant proposals talk about beyond lambdactum frameworks with cautious excitement. Others sense history repeating, old paradigms giving way only when necessity crushes elegance. And yet, beneath every abstract slide and cautious headline, there's a shared emotional current, humility. The same humility that followed the supernova discoveries of 1998. Once again, the universe has reminded us that our models are temporary conveniences, not commandments. The deeper we measure, the more provisional truth becomes. Physics built its empire on constants, numbers that define, guide, and reassure. Now one of those numbers may be moving, and the empire trembles accordingly. DESI hasn't only complicated the science of expansion, it has exposed the fragility of belief within science itself. As one astronomer put it, half smiling, half stunned, we thought we'd mapped the universe. Turns out it's mapping us instead. The great alternatives. When a theory starts slipping, physicists don't surrender, it's not in their nature. They start sketching escape routes. By the end of 2025, as DESI's data provoked sleepless nights and frantic recalculations, talk at conferences turned from disbelief to design. If lambdactum was cracking, what could replace it? On whiteboards and preprint servers, one phrase appeared again and again: dynamical dark energy. The simplest version of that idea is quintessence. Imagine that dark energy isn't a constant vacuum pressure but a field, like an ocean whose tides shift over cosmic time. That field rolls slowly down a potential slope, its energy density evolving as the universe expands. In some epochs it pushes harder, in others only gently, producing the expansion history DESI hints at. It's elegant. One equation replaces a fixed constant with something alive, responsive. But it comes at a cost: extra parameters, fine-tuning, and a question that's never resolved. If quintessence changes with time, what sets its pace? What stops it from collapsing entirely or blowing up? Then there's its unruly sibling, phantom energy, a form of quintessence turned up beyond stable boundaries. In this scenario, the pressure is so negative it accelerates expansion faster and faster until, eventually, galaxies, stars, atoms, even space-time itself tear apart. Cosmologists call that in the Big Rip. It's theatrical but mathematically consistent. Phantom energy fits certain interpretations of DESI's trend if dark energy's force grows with time rather than fades. Instead of gravity reclaiming the cosmos, space stretches itself to shreds. The horrifying beauty is that both extremes, crunch or rip, now sit on the same sliding scale, driven by how this one parameter, W, evolves. Quintessence, phantom energy. Their first-order fixes, built to tweak lambdactum without discarding relativity. But some physicists think the real answer lies deeper, in gravity itself. Maybe the universe doesn't need new energy. Maybe Einstein's equations need a subtle rewrite. Enter modified gravity theories. The most studied is FR gravity, a model where the famous Einstein-Hilbert action gains an extra term, a function of spacetime curvature. The modification behaves from a distance a lot like dark energy, driving acceleration without a cosmological constant. At cosmic scales it works. At solar system scales it struggles to hide its footprints. Others push further. MOND, modified Newtonian dynamics, started as an attempt to replace dark matter, not dark energy, but its cousin TVS, tensor vector scalar gravity, grew into a full relativistic framework. TVS can mimic cosmic acceleration, yet fails to reproduce the fine grain of the cosmic microwave background. Each attempt fixes one symptom and breaks another, like trading flat tires on an endless race. Then come the bimetric and scale invariant theories, the wild frontier of cosmology's imagination. Bimetric models posit two interacting metrics, two fabrics of spacetime woven together. Matter lives on one, gravity pulses through both. Their interference can create an effective cosmological constant that changes with time, exactly what DESI seems to detect. Scale invariant ideas go further, suggesting the universe has no true length scale at all, that constants like Newton's gravitational strength evolve naturally as the cosmos ages. Under those rules, a constant, lambda, would be impossible by definition. Space curves and stretches within its own self-similar geometry, producing what looks like dynamic dark energy without inventing a new entity. Still, none of these frameworks survive every observational test. You fix one tension and watch another emerge. Modified gravity tends to predict either too much lensing or too little structure. Quintessence fits DESI but unnaturally tunes its potential. Each alternative demands extra complexity that borders on theoretical heresy, new particles, hidden fields, or untested coupling constants. To skeptics, it feels like swapping one mystery for three others. Yet the appeal persists because every traditional comfort is eroding. The fine-tuning problem, lambda's impossible smallness, may vanish if it isn't really a constant at all. The coincidence problem, why dark energy and matter are comparable today, finds relief if energy slowly transfers between them. Dynamical models naturally produce epochs of near balance as the cosmic field adjusts. It's seductively tidy, though often too flexible to falsify. Meanwhile, data analysts chase their own alternatives. Hybrid fits combining evolving dark energy with subtle curvature, or dark sector coupling that lets dark energy siphon momentum from dark matter. The latter can smooth out DESI's overgrown cluster predictions, explain the sigma-8 tension, and still keep the expansion curve plausible. These aren't fantasies anymore. They're equations in serious journals. The tone at symposia has shifted from which model replaces lambdactum to which version of evolution survives the next dataset. For younger researchers, this upheaval feels invigorating. For veterans, it's déjà vu of 1998, the unsettling thrill of seeing physics reinvent itself. They recall when cosmic acceleration itself sounded implausible, dismissed until supernovae forced belief. Now dark energy's evolution triggers the same reflex, skepticism fighting wonder. One cosmologist compared it to standing on a frozen lake hearing the first crack, the sound more terrifying, because it means the surface was never solid. Not every alternative begins with equations. Some verge on metaphysics. A few theorists, drawing from quantum gravity and holographic principles, propose that dark energy isn't a substance or field at all but a back reaction, a statistical effect of many gravitational interactions averaging out. Others toy with the idea of a mirror universe containing negative energy that cancels ours half a cycle behind. In their math, cosmic acceleration results from twin realities tugging at each other through shared geometry. These sound like science fiction, but they echo serious attempts to reconcile relativity with quantum mechanics. If the vacuum is dynamic, it might communicate with unseen dimensions or parallel metrics we only perceive as dark energy's ebb and flow. The uncomfortable truth is that every credible explanation drags physics toward its oldest dream, a unification of the large and the small. To make dark energy evolve coherently, you have to blend quantum fields with general relativity's geometry, and that's the very junction where current theory fails. The alternatives don't just replace lambdactum, they force us into new mathematics where spacetime and energy exchange roles, where constants emerge from interactions instead of dictating them. As papers multiply, quintessence potentials shape like rolling hills, TVS variants tuned for lensing, biometric couplings polished to pass solar tests. The community divides itself into cautious realists and bold architects. The realists want hard confirmation before abandoning the constant. The architects believe waiting for certainty risks stagnation. Between them lies the unspoken fear that maybe there is no single replacement waiting to be discovered. Maybe the universe resists neat closure. Maybe its acceleration was never one phenomenon, but a shifting interplay of many. Whichever camp you favor, the direction is clear. Simplicity has left the building. Cosmology's clean equations are giving way to adaptable frameworks, models with knobs that turn as the data evolve. Some call that messy, others call it maturity. When observation refuses to fit our simplest story, it means we've started asking questions big enough to deserve complexity again. By early 2026, one commentator summed it up neatly in a conference review. Lambdactum was a chapter of clarity. What comes next will be a library of possibilities. And within that library, the scariest and most exciting thought persists. The universe might not be underwritten by constants at all, only relationships. DESI didn't just nudge cosmologists to invent alternatives. It reminded them that alternatives are the essence of science. For every law that cracks, another explanation waits in the dark, evolving just like the energy it seeks to describe. The conspiracy of certainty. There's a quiet rumor that passes through every generation of scientists, not about cover-ups or corruption, but about comfort. The idea that once a model works too well, it stops being questioned. In cosmology, that rumor has a name, lambdactum. It reigned for a quarter century not because it was simple, but because it was beautiful. Its constants matched the data, its equations closed elegantly. And in science, elegance can be addictive. By the early 202s, questioning the model felt almost inappropriate. Its parameters were carved into simulation codes, its predictions taught to first-year students like biblical facts. Funding proposals lived or died by how neatly they fit inside its framework. Lambdactum had become the operating system of cosmology, stable, trusted, and nearly invisible. So when whispers of discrepancy began, the community's first instinct wasn't curiosity, it was defense. In seminar rooms, skepticism wore the tone of reassurance. It's statistical noise. Systematics will smooth it out. A few sigma doesn't rewrite physics. Those were the mantras passed around while DESI compiled data that refused to behave. To admit the possibility that the constant might not be constant was to question the foundation of thousands of careers, entire missions. Not remotely a conspiracy, just inertia polished over decades of confidence. Still, some younger scientists couldn't shake the feeling that the field had drifted from inquiry to maintenance. They'd read literature reviews that treated lambdactum like sacred architecture. Here's the cosmological constant, here's the cold dark matter, here's the fitted curve that never misses. Every anomaly, Hubble tension, sigma 8 tension, low quadrupole, was explained away as instrumentation. The standard model wasn't wrong, just perpetually under refinement. Then DESI broke that rhythm. What the telescope delivered wasn't just noise. It was a statistically coherent pattern that lined up with earlier hints. As data technicians double-checked results, senior scientists cushed their discomfort behind professionalism. Preliminary evidence, they'd say on stage, voice carefully neutral, while slides projected curves bending in ways they weren't supposed to. Beneath that restraint, you could feel something tightening, a recognition that the walls of their mental universe were flexing. Privately, the conversations were raw. Either the universe changed, one researcher said during a late-night video call, or we've been seeing it wrong all along. No one thought the laws of nature literally transformed overnight. They were admitting something subtler, that their faith in constancy might have blinded them to motion hiding in plain sight. It's tempting to imagine a cover-up, some secret cabal of cosmologists protecting prestige. But the truth is more human. The loyalty wasn't to dogma, it was to success. Lambdactum worked. It predicted the cosmic microwave background with uncanny accuracy, mapped galaxy clustering almost perfectly, folded chaos into 6 convenient numbers. Walking away from that elegance felt like betrayal. When data clash with such a tidy story, the instinct isn't denial, it's grief. And yet, progress in science has always depended on the uncomfortable few willing to challenge consensus from within. In the early 200s, those voices were fringe, writing papers on evolving dark energy that nobody cited. Now, suddenly, they're the reference point. The same institutions that once ignored them are quietly funding their conferences. Paradigms shift not by votes, but by generations. Still, institutional momentum is a real force. Research grants favor continuity. Large telescope collaborations must justify billion-dollar budgets by promising to refine existing models, not overthrow them. When your team has decades of data investment riding on one framework, exploring an alternative feels risky, even reckless. The irony is that the more successful a model becomes, the harder it is to replace, because careers, instruments, and entire research economies orbit its gravity. So the conspiracy in cosmology wasn't secrecy. It was consensus, an overgrown confidence that mistook agreement for truth. For years, minor mismatches were smoothed over under the phrase, probably systematics. Now DESI's numbers sit stubbornly within the margin where excuses go to die. The data may wobble, but their direction holds. There's something almost confessional about how physicists talk now. You hear phrases like, we might have over-interpreted consistency, or maybe lambdactum was a map, not the territory. They aren't dismantling the model out of rebellion. They're acknowledging that reality never signed their equations. The universe doesn't owe them neatness. Conferences have grown strangely self-aware. A keynote speaker jokes, "Welcome to year X of the model that survived everything except data." Laughter follows, nervous but genuine. Scientists laugh because they recognize themselves in that line. They see how certainty can masquerade as understanding, how human psychology seeps into the march of reason. Cosmology isn't unique in that. Every scientific revolution arrives with a trail of tidy excuses for why it shouldn't have happened sooner. Newton resisted wave theory. Einstein resisted quantum mechanics. Entire fields cling to stability until the cracks spread faster than justification can fill them. DESI is simply this generation's reminder that no law lives forever. One historian of science recently noted that revolutions rarely feel revolutionary when they begin. They start as routine recalibration, cautious phrasing, incremental updates. Only decades later do textbooks draw a line and call it a turning point. Right now, cosmology sits somewhere between denial and acceptance, a civilization realizing its gods are parameters and its priests are data analysts. Inside research institutes, postdocs whisper bolder theories over coffee, while older mentors urge restraint. Wait for Euclid, they say, for Rubin, for Roman. Let the next wave confirm. It's practical advice, but you can sense the fatigue in it, the weariness of having to defend a model that still works but might not deserve loyalty anymore. And so the field finds itself in a liminal state, half faithful, half free. No one is burning the old equations, they still describe most of what's observed. But they now do so under probation, their once sacred constants tagged with mental asterisks. When press releases quote cosmologists claiming the standard model remains robust, what they mean is, we're scared to live without it. The irony is that DESI's disruption isn't killing science's credibility, it's revitalizing it. For the first time in years, papers are thrilling again, speculative, risky, imaginative. Conferences buzz with the same tension that followed the 1998 supernovae, disbelief laced with wonder. Scientists are doing what they were built for, doubting, revising, chasing better explanations. That's not collapse, that's awakening. And maybe that's the real conspiracy. Not paperwork or politics, but the quiet psychology that makes humans crave certainty in an uncertain universe. We built lambdactum to tame chaos, then mistook our control for truth. Now the cosmos is handing reality back, messy, variable, alive. No wonder some scientists stare at DESI's plots with equal parts terror and exhilaration. The data don't just append their equations, they expose the limits of their confidence. Every spike and curve whispers the same message: you were never meant to be certain. When the next generation of observers, Euclid, Rubin, SPHEREx, confirms or refutes these hints, cosmology will adapt again. The real story isn't about whether dark energy evolves, but whether science still knows how to. Because in the end, the only constant more dangerous than a cosmological one is the human need for one. Ghost data and digital universes. In science, every precision instrument creates ghosts, bits of data that don't fit. Usually they vanish after calibration, but sometimes they linger, taunting the analysts who find them. When DESI's results began hinting that dark energy might be evolving, teams across the world dove into the numbers hunting those ghosts. They weren't looking for errors anymore. They were searching for meaning. The deeper they went, the stranger it became. Simulations built to replay DESI's measurements started showing residual patterns that shouldn't exist, tiny correlations in galaxy clustering that refused to wash out even after the models were refined. Researchers called it ghost data, partly as a joke, partly because no one could pin down its source. It wasn't random noise, yet it didn't behave like any known background effect either. The implication was unnerving. Maybe the ghosts weren't mistakes in the data, but messages from physics itself. Get this, some supercomputer runs suggested these anomalies trace back to how dark energy might interact with the quantum vacuum. In most simulations, space is treated like a silent stage where matter performs. But a few groups, blending general relativity with quantum field approximations, allowed that stage to ripple. What came out looked alive. Expansion rates oscillated ever so slightly, as if the universe exhaled and inhaled over cosmic epochs. Statistically small, but persistent. And those fluctuations matched the mild wiggles DESI recorded in the expansion timeline. That's where speculation exploded. Could the vacuum, what we call dark energy, be a dynamic system reacting to the cosmos it drives? If so, the universe might not just be evolving, it might be learning. Every structure formed, every cluster, every void, feeds back into the vacuum's energy field, modifying it. The universe becomes self-referential, constantly adjusting its own parameters. For theorists used to constants chiseled in stone, that idea borders on heresy. Yet it fits DESI's results disturbingly well. To visualize this, Teams fed the evolving dark energy parameters into Japan's Fugaku supercomputer, one of the only machines fast enough to simulate billions of interacting particles under changing cosmological conditions. The output looked nothing like the standard Lambda runs. Instead of an orderly web expanding outward, the simulated cosmos pulsed. Filaments brightened and dimmed. Clusters drifted slightly as though tugged by unseen tides. When compressed into short animations, you could almost mistake it for a living organism's heartbeat. Scientists call this feedback cosmology. The idea is that as matter clumps, it curves spacetime differently, which in turn changes how dark energy behaves locally. Those regional responses accumulate, producing global evolution, a cosmic echo chamber. Some even propose that dark energy's apparent variability could be a statistical illusion born from that feedback. In this view, the universe isn't changing its laws, it's revealing their complexity through interaction. Still, others push further, wondering if these feedback signals hint at something larger, connections between cosmology and the quantum realm. A few papers argue that what we perceive as dark energy could be an emergent effect of entanglement on vast scales. Space itself might store information, and the more structure it contains, the more its energy balance shifts. Imagine the universe as a digital network where each galaxy is a node, each filament a thread of information flow. As the network evolves, its energy distribution updates, just like code rewriting itself mid-run. Those analogies may sound like poetic metaphors, but they stem from real mathematics. Quantum gravity researchers exploring holographic principles have demonstrated that spacetime geometry can emerge from quantum information patterns. If that's true, DESI's evolving dark energy might simply be the macroscopic signature of microscopic computation, a feedback loop where the universe's data structures dictate its physical expansion. The ghost data in that sense aren't errors, they're residuals of a deeper algorithm at work. The notion bends minds and divides rooms. Some physicists embrace it, saying it could finally bridge general relativity in quantum fields. Others dismiss it as premature philosophy disguised as science. Yet both camps keep staring at the same numbers because, so far, no conventional model explains them better. The anomalies persist through independent datasets and alternative reduction pipelines. They're not going away. Meanwhile, every new DESI run only deepens the mystery. Each time the instrument maps another slice of sky, it adds millions of new galaxies, each with precise coordinates and redshifts. Feed those into simulations and patterns repeat, not identical but recognizable. Slight shifts that behave almost like harmonics of a cosmic signal. A few researchers joke that if you could translate them into sound, the universe might literally be humming. The joke lands because it feels plausible. All this uncertainty drives innovation. Teams are developing machine learning algorithms to identify subtle signatures of evolving dark energy within otherwise chaotic data. These AIs comb terabytes of cosmic maps, detecting patterns too complex for humans. In test runs, some networks flagged regions where the statistical behavior of galaxy clustering changes with redshift more than expected. When compared to DESI's real data, those regions aligned surprisingly well. Machines, free from theoretical bias, appear to sense something physicists are still struggling to define. And that's where the language of ghosts shifts meaning. It no longer refers to measurement errors. It describes knowledge gaps taking shape in real time as software and data outpace human intuition. DESI's findings are forcing cosmology into a new rhythm, where observation races ahead of theory. Simulations grow so detailed that interpretation struggles to keep up. The cosmos is being rendered faster than it can be understood. Philosophically, that realization lands heavy. What if dark energy isn't a discrete entity at all but the statistical behavior of a system too large for our brains? What if the reason constants appear to change is that they were never universal, merely averages of a reality far richer and more mutable than our mathematics imagines? It's an unsettling thought. The universe might be consistent only in the long run, chaotic in the small, and we're small. Some researchers hint that human comprehension might have reached its event horizon, the boundary beyond which patterns exist but interpretation fails. Others push back, insisting technology will extend that frontier. Future instruments, quantum interferometers, even deeper spectroscopic arrays, may reveal the underlying code of cosmic evolution. The very pursuit of that code transforms science from an act of discovery into one of translation. Late nights in computing labs, you can feel both awe and frustration. Monitors glow with simulations of galaxies swirling like neural clusters, energy nodes flickering like thought. Someone inevitably murmurs, "What if this is how the universe remembers?" No one answers, because it's impossible to tell if that's poetry or physics now. And maybe that's the point. The ghost data exist precisely at that border, between measurable and meaningful, between math and metaphor. They remind scientists that even with billion-dollar telescopes and planet-sized computers, they're still reading shadows cast by something larger. Where theory falters, observation keeps unspooling its silent story. Each line of data stretched across time becomes a thread in a cosmic fabric we barely perceive. DESI maps the threads, simulations animate them, philosophy tries to catch up. Whether the result is dynamic dark energy, quantum feedback, or an emergent dimension we can't yet name, one lesson endures: the universe never stops surprising the instruments created to explain it. For now, cosmologists stand amid the hum of servers and the whisper of desert wind outside observatories, peering into code that resembles cosmos and cosmos that resembles code. Between them flicker ghosts of understanding, half-formed but persistent, a reminder that the ultimate dark energy may be ignorance itself, evolving as fast as the universe expands. The next generation of watchers. At the edges of deserts and in orbit high above Earth, a new generation of instruments waits to test DESI's revelation. They're the successors, each one designed not just to map the universe but to interrogate it. Together, they form the largest observational alliance ever built, united by a single question: is dark energy truly evolving? First comes Euclid, the European Space Agency's flagship mission launched in 2023. From its position nearly 1 million miles from Earth, Euclid peers deep into space with two powerful eyes, one tuned to visible light, the other to infrared. Its goal is to map billions of galaxies, measuring how their shapes distort under gravity's pull. Those subtle warps, called weak lensing, reveal how matter clumps and how dark energy stretches spacetime around it. If dark energy changes strength across cosmic time, Euclid should see the pattern inscribed in the geometry of those distortions. Then there's the Vera C. Rubin Observatory in Chile, a telescope so ambitious it plans to image the entire visible sky every few nights. Its survey, the legacy survey of space and time, will collect billions of galaxies, supernovae, and variable stars. Each snapshot becomes a frame in a decade-long movie of cosmic motion. Rubin's specialty is time, tracking how brightness and position evolve. Every time a distant supernova flares, it acts like a cosmic beacon. The way that light fades through expanding space offers a direct probe of how fast the universe stretches. Combined with DESI and Euclid, Rubin's data will let cosmologists trace expansion with a precision that makes past surveys look like sketches. Orbiting just a few years away from launch is NASA's Nancy Grace Roman Space Telescope, Hubble's powerful heir. With a field of view 100 times larger than Hubble's but similar clarity, Roman is built for panoramas. It will measure the cosmic distance ladder through supernovae and baryon acoustic oscillations, cross-checking DESI's results from above the atmosphere's distortions. Its job is confirmation, to decide if the shift DESI detected is an illusion of noise or a sign of evolution written into spacetime itself. Closer to home, the SPHEREx mission waits on its final tests. Its full-sky spectroscopic survey will catalog more than 400 million galaxies in near-infrared light, mapping the large-scale pattern of matter with different methods than DESI. Think of it as the wide-angle counterpart to DESI's precise zoom. By pairing their measurements, scientists can check whether the apparent evolution of dark energy depends on direction, epoch, or wavelength. If those dependencies appear consistent, the conclusion strengthens. Dark energy isn't constant, it's alive. And though its primary mission focuses elsewhere, the James Webb Space Telescope contributes quietly, pushing the frontier of observable galaxies farther back in time. By comparing the earliest structures Webb finds with predictions from evolving dark energy models, cosmologists can test whether early clustering aligns with DESI's hints. If those newborn galaxies formed earlier or differently than Lambda forecasts, it'll lend further weight to the idea that cosmic acceleration has been changing since the universe's infancy. In control rooms and mission briefings, coordination among these telescopes looks more like orchestration than competition. NASA, ESA, ground observatories in South America and the United States each tunes to a different part of the cosmic symphony. Euclid measures space's shape, Rubin captures its motion, Roman checks its tempo, and DESI keeps the beat from the desert. Their data will cross-calibrate constantly, forming what scientists half-jokingly call a watcher's network, a web of eyes staring into the universe's past to understand its future. Behind those missions lies a technological story of obsession. Modern cosmology runs on precision optics, cryogenic detectors, and algorithms that digest petabytes of starlight. Teams code software to align fiber optic plates within microns and simulate atmospheric turbulence down to the photon. Every lens polished, every error reduced, nudges humanity a fraction closer to decoding the vacuum's secret language. But along with precision comes pressure. The community feels it, the sense that confirmation or refutation of DESI's findings will determine the next decade of cosmology. If Euclid and Roman see the same pattern, the same subtle deviation in expansion history, the revolution begins. If they don't, Lambdictum survives but scarred. Researchers joke that entire careers hang on a single parameter, the equation of state W wandering just a little off -1. Still, there's excitement that borders on reverence. For the first time, we're within reach of measuring dark energy's behavior directly rather than inferring it from cosmic leftovers. The instruments are so sensitive they can detect fractional shifts in lensing angles no wider than a strand of hair seen from a mile away. That sensitivity transforms cosmology from theoretical speculation to experimental science. When Roman's wide-field camera or Rubin's gigapixel array sends back its crush of images, it won't just confirm numbers, it will show whether the universe breathes. Scientists talk candidly now about a golden decade. Between 2023 and 2033, these missions will map more of the sky in deeper detail than all previous astronomy combined. Cross-matching their catalogs could uncover whether the density of dark energy is creeping upward or declining, and at what rate. Each new survey becomes another timestamp in a story stretching from the Big Bang to the far future. And amidst the coordination meetings and data pipelines, a quieter transformation unfolds. The community that once clung to certainty has rediscovered curiosity. Postdocs who grew up under the shadow of Lambdictum now design tests to break it. Principal investigators who spent decades defending constants are proposing models where none remain fixed. A cautious optimism runs through presentations, as if science itself is exhaling after years of holding its breath. For ordinary observers, that shift may sound remote, but its consequence is profound. These telescopes don't just measure galaxies, they measure fate. Every photon from a receding cluster carries an encoded answer about the cosmos's future temperature, density, and lifespan. When Euclid lenses those photons or Rubin catches a new supernova, the data they collect are effectively letters from the universe about its own destiny. Back at Kitt Peak, DESI keeps feeding that conversation. Night after night, it adds more points to the expanding map. Soon, the next generation of watchers will join, layering their perspectives until the cosmic story either coheres or cracks further open. Among the scientists waiting for results, anticipation feels almost spiritual. There's fear of error, of ignorance, but also awe. As one astrophysicist put it over coffee before Euclid's launch, whatever the truth is, we'll see it soon. And once we do, we'll never see the universe the same way again. Maybe that's the real accomplishment of this golden decade, not the data itself, but the humility it restores. For centuries, humanity has looked up and sought permanence. Now, telescope after telescope tells us that even the emptiness between stars is changing. We are witnessing the universe in motion, not just through space, but through its own laws. When those final results arrive, whether they confirm DESI's shock or quiet it, they'll decide more than the universe's fate. They'll decide ours, how we understand change, constancy, and our place in a cosmos that's still writing its own script. The end of certainty, the start of understanding. By the time the dust settles and data stops shifting, something unexpected happens. The fear that gripped cosmology, the dread of being wrong, gives way to quiet awe. It's not defeat, it's discovery. Scientists begin to realize that uncertainty was never the enemy of understanding. It was the price of progress. The early headlines fade, replaced by deeper reflection. What does it mean that dark energy changes? What does it say about us that we assumed it could? For decades, cosmology told a comforting story. The universe began, expanded, and would end predictably. Now that story has cracks, but through them comes light, new questions, new ways of seeing. In lecture halls and observatories, conversations sound different. Researchers no longer chase constants, they chase context. They talk about relationships, how matter, energy, and geometry might co-evolve rather than exist apart. A fresh humility seeps into their tone, the humility that comes from realizing precision isn't the same as truth. For students entering the field in the wake of DESI, lambdacom isn't gospel anymore. It's a chapter. They study it as history, a brilliant simplification that served its era. Their mentors, once guardians of that simplicity, now encourage them to think wider, to expect shifting answers. The next generation of cosmologists is growing up fluent in uncertainty. That's the quiet miracle DESI sparked. It reminded everyone that science moves forward not by defending certainty, but by confronting the next unanswered question. The data might keep changing, but so does understanding. Every revision is progress disguised as doubt. You can feel that transformation in the tone of scientific papers. Gone are the conclusions that read like verdicts. In their place are phrases that breathe curiosity. These findings suggest, this may indicate, further investigation required. It's not hesitation, it's honesty. The universe has outgrown the comfort of simple explanations, and humanity at last seems ready to follow. Think back, only a generation ago, dark energy itself was a shock. Then came acceptance, equations, and complacency. Now this new twist, its evolution, proves that comprehension never ends. Each solved mystery births a bigger one. In a sense, the universe keeps teaching the same lesson. Permanence is an illusion. For the first time in decades, cosmology feels young again. The big questions are back on the table. What is space? What is time? Does the vacuum pulse? Conference halls that once traded minor parameter updates now buzz with imagination. The uncertainty that once terrified physicists now energizes them. You can see it in the small human moments. A postdoc staring at simulation outputs at dawn, whispering that nothing constant might be the most beautiful phrase in physics. A grizzled professor, long skeptical of revolutionary claims, admitting into a microphone, "I suppose we should have expected the universe to surprise us again." Laughter follows, the good kind, the relieved kind. The kind that says, we're learning. Historians of science will one day look back at this period not as collapse but as correction. DESI's discovery didn't destroy theory, it recalibrated ambition. It reminded cosmology that no measurement, however precise, defines reality forever. Models are scaffolds. Knowledge is temporary architecture awaiting its next renovation. And for the rest of us, people standing on a small planet orbiting an ordinary star, the implications are strangely comforting. Because if even the universe's laws can evolve, maybe change isn't chaos. Maybe it's nature's rhythm. The cosmos isn't drifting toward ruin, it's continuing to create possibilities. The story isn't done. In public talks, astrophysicists start using different metaphors. They no longer call the universe a machine or a clock. They call it a conversation, a dialogue between energy and gravity, matter and emptiness, measurement and meaning. That shift, subtle but profound, reframes everything. The cosmos isn't something done, it's something doing. The emotional arc is complete now. Shock turns to confusion, confusion to exploration, and exploration to gratitude. These researchers aren't humbled by defeat, they're exhilarated by mystery. Dark energy, once seen as a problem to solve, becomes a partner in discovery. Every flicker of uncertainty is an invitation to look deeper. Meanwhile, DESI keeps scanning, adding galaxies to its map. Each new coordinate extends the record of existence a little further, a reminder that our species is capable of measuring the universe's pulse from a mountaintop on one tiny world. That alone feels miraculous, an act of curiosity written across billions of light years. Euclid, Rubin, Roman, SPHEREx all continue the search. Whether they confirm or contradict one another hardly matters now. The real victory is that humanity dared to ask the question in the first place. Is reality as fixed as we thought? The answer, whatever form it takes, will reshape more than physics. It will reshape perspective. Because here's the quiet truth emerging from all this upheaval. The universe isn't broken. It was never meant to obey our need for simplicity. What's breaking, slowly and beautifully, is our confidence that certainty is the same as understanding. In a decade defined by measured revolutions, DESI's Shockwave stands apart. It didn't just show that dark energy might evolve. It showed that knowledge itself must evolve to survive. From the first astonishment of 1998's supernovae to the precision of 2025 spectra, we've traveled from knowing that the universe expands to questioning how it expands, and why. That's not regression, it's maturity. The deeper pattern reveals itself. Every solved equation opens a doorway wider than the one before. Every settled law invites a deeper chaos. The rhythm of discovery never slows, it only changes measure. And in that rhythm, humanity finds purpose again, not in answers, but in pursuit. As the cameras inside DESI pivot toward another patch of sky, photons from ancient galaxies strike its sensors, news from billions of years ago, arriving just in time to remind us that understanding is always unfinished. In their faint glow lies both history and prophecy. We may never hold the final truth, but maybe that's the point. Maybe the cosmos keeps its last secrets not to mock us, but to keep us moving. The desire to know is the ember that burns against infinity. So when historians write about this era, they'll say that DESI taught us something bigger than any constant or field. It taught us humility at cosmic scale, that the more precisely we measure the universe, the more it teaches us to measure ourselves, our biases, our assumptions, our need for permanence. The universe isn't fragile, our certainty is. And maybe that's what saves us. Because as long as everything we know can still change, there's always more to learn. The final truth: the universe isn't breaking physics, it's evolving meaning. It isn't a problem, it's a process, infinitely self-correcting, just like science itself. The universe isn't broken, it's teaching us how much more there is to learn. If you want to see how these discoveries connect to tomorrow's horizon, and what happens if the expansion really does stop, subscribe and watch our next story. The day the universe stops expanding.